You open a malicious script and find 3,000 lines of JavaScript that look like unreadable noise. Attackers use this noise to hide their payloads from security scanners. The MITRE ATTK framework categorizes this as technique T1027, obfuscated files or information. This strategy has one unavoidable vulnerability. To actually execute, the browser must eventually convert the noise back into plain text. This process almost always flows through the eval function. Your tactical objective is to intercept the decoded string in that narrow window between the decryption routine and the final execution. Targeting this execution bottleneck provides a reliable path through any layer of encryption or obfuscation an attacker chooses to deploy. To choose the right decryption strategy, you must first identify the pattern of obfuscation. Base64 encoding is the most common. Look for long alphanumeric sequences ending in equal signs. String concatenation splits the payload into fragments joined by numerous plus signs. Character codes use numerical arrays that translate into letters at runtime. Variable renaming replaces logical names with hex-like identifiers to confuse human readers. Decode involves inserting unreachable logic blocks to artificially inflate the file size and exhaust analysis tools. Nested eval loops place multiple decode calls inside each other to create layers of protection. And replace chains use a search and replace function to strip out dummy characters and reveal the true string. No matter how many of these 7 patterns are layered together, they all eventually reach the same execution point. In the browser, you can use a console overwrite to trap the script before it loads. By redefining the eval function, you force the browser to print the decoded code to your console instead of executing the malicious payload. For more granular control, you use manual breakpoints. Open the DevTools Sources tab and locate the script containing the obfuscation routine. You can manually pause the browser right before the payload runs by setting a breakpoint directly on the eval line. Investigating the paused argument in the scope panel reveals the decoded strings and current variable values in plain text. Overriding is a fast way to automate the trap, while breakpoints allow you to manually dissect complex, multi-stage payloads. If you need to decode a script without running it at all, CyberChef allows you to build a recipe to process Base64 or URL-encoded payloads offline. Let's apply these steps to a real-world example. This input contains a mix of hex escapes and character codes. First, resolve the hex escapes to reveal the standard URL protocol. Then, convert the character codes to identify the target DOM property. Reassembling the variables reveals the true command. Dismantling these layers transforms unreadable noise into an actionable indicator. Even with the right tools, some payloads will refuse to run. This is caused by environmental keying. Malicious scripts often check system properties like browser language, screen resolution, or referrer URLs. If your analysis environment doesn't match the expected profile, the payload simply exits. You bypass this by manually spoofing the required properties in the console before the script runs. Ensuring the environment matches the attacker's expectations is the final step to forcing the payload to reveal itself. The result of this process is the isolation of the hidden destination URL, allowing you to update network block lists. This methodology relies on a consistent workflow, using DevTools for execution management, CyberChef for static transforms, and the eval function as the primary point of interception. You can apply these techniques in a dedicated lab environment by visiting learn.epic0.net. Understanding the browser's inherent execution constraints ensures that even the most complex obfuscation remains a solvable technical problem.